Hello everyone. So I'm here today with a vectors question sent to me by a student. So we'll be working through this today. So here we're given a trapezium and we're given a few different vector lengths. We know that AB is 5A, C to B is B, and D to C is 3A. And now we're given here that AX, which is this length here, is equal to lambda of AC. So here lambda is just a constant. It's just a constant. And we can see from this example that lambda clearly must be less than 1 since AC is this entire length. And so AX has to be a fraction of that, which needs to be less than 1. And similarly, we have that dx is equal to mu of d to b. And again, we have the same situation where this constant mu must be less than 1 since dx is just a fraction of a db. But for the first part, all we have to do is find, in terms of a and b, a to d. And to find the vector a to d, what we do is we take a path that will take us from the point A to point D. It doesn't matter which path we take, but it's best to use the vectors that we already know. So to go from A to D, we start at point A, and we can take this vector AB, which gives us 5A, and then we add on this vector BC. And now we note that CB is equal to B, and therefore BC, to go in the other direction, is always the negative of whatever it is. So here it's negative B, we're adding that to the 5A. And finally we go from C to D. And again, we know that DC is 3A. So going from the other way, CD would be negative 3A. And then we add that to this vector sum. So we've effectively shown here we're going from point A to D using the points B and C as well. And then that gives us a final vector of 2A minus B. And now part 2 of this first question is to find the vector D to B. Again, we just use a vector path. So first we go from D to C, which gives us 3A. And note how I'm underlining these letters A just to separate it from a variable A, because this is a vector here. And it's good practice to do that in the exam as well. So anyway, we're going from D to C, which gives us 3A, and then we're going from C to B, which is plus B. And then that will take us from the point D to the point B. From the point D to the point B. Okay, so that is the first part of the question done. Now the next part of the question requires us to use these constants, lambda and mu, and to find AX. So from the question, we're given that AX is equal to lambda of AC. So if we find AC, we can just multiply it by lambda to find AX in terms of lambda. And we know that AC using a vector method is 5A minus B, to go from B to C. So AC is equal to 5A minus B. Therefore, AX is equal to lambda of 5A minus B. And then part 2 of this is to find dx. And we're given in the question that dx is equal to mu times db. And from part 1, we know that we've solved already that db is equal to 3a plus b. And so all we have to do is state that dx is equal to mu of db, which is 3a plus b. Okay, so that's that done. Now we move on to the final question. This is a very tricky question that could come up in the paper 4. It's a paper 4 style question. It's where we now have to find the value of lambda and mu. And the way we do that is, the general tip for this type of question is to find one vector and find two different paths to get to the vector. So in this instance, if we use the previous parts from the question, we know that ax is equal to this, lambda times 5a minus b, and that dx is equal to this. So if we use this information, we can find out that we can find one vector and represent it using two different ways. And so one way to do that is we use the vector dx that we already know is equal to mu times 3a plus b. And so that's one way of getting there, one path. And now we have to find another path so that we can solve simultaneously. And we very quickly see that another path to go to from d to x is first by going through a, so dA plus ax. And then we can equate the two. So this is our second. And then we can equate the two and solve for lambda and mu. And I'll work through that too. So if we just write that down here, we know that dx is equal to dA plus ax. Now what's dA? So from the very first question, we found AD is equal to 2a minus b. And so if you remember, if we have some vector that is, so in this, for example, if we know that CB is equal to B. And what I mentioned earlier in the video is that if we go in the opposite direction, it's always the negative, or whatever the initial vector is. So therefore, dA is the negative of A to D. So therefore, it's equal to negative of 2a minus b, what we found in the first question. Negative 2a minus b. And now we have plus ax. We've already solved for that in terms of lambda. So we can add that here, which is equal to lambda 5a minus b. So now this is equal to dx. But remember from the previous part, we found already that dx is equal to this in terms of mu. So we can substitute in that here. We can substitute that in here. And we can now equate the two and say that mu of 3a plus b is equal to this expression right here. Because both will give us the vector d to x. So now this is where the challenging part comes. What we firstly do is we will tidy up this right hand side. So mu of 3a plus b is equal to negative 2a plus b. Remember to expand out the negative sign. Plus lambda of 5a minus b. And that is equal to, if you write this in terms of a and b, this is equal to negative 2 plus 5 lambda times a plus 1 minus lambda times b. This is the same. You can verify that by just expanding it out. All we've done is found two different parts of the expression, but making a and b the main components. And if you expand it, you'll get the exact same thing as this above. It's just, you'll see why I've done this. It'll make problem solving easier later. And on the left hand side, we have 3 mu for the component A and just mu for the component B. So now this is the expression we're dealing with. So how do we proceed from here? And this is where the a very important concept that you need to know, which is known as comparing coefficients. Comparing coefficients. And this is how we'll solve for this. So essentially what we have is, if we have these two equations with different vector parts to it, we know that the component part of A in both vectors must be equal. And similarly, the component part of B of both vectors must be equal. And what that tells us is that 3 mu is equal to negative 2 plus 5 lambda. They must be equal. And similarly, mu is equal to 1 minus lambda. Because only if they are equal will the vectors be the same. And only if they are equal will we get two vectors that give us the same dx. Remember, this is the same vector. So what we're doing here is comparing coefficients or equating coefficients. And this is how you would solve this tricky vectors question. So what we do is we set up a simultaneous pair of equations. For the component part of A, we know that 3 mu must be equal to negative 2 plus 5 lambda. And that's our first pair of equations. That's our first equation. And from the component part from B, we get that mu is equal to 1 minus lambda. And that's our 2. And now you can solve this simultaneous equations, this pair of simultaneous equations like you normally would. So what I'm going to do here is multiply 2 by 3 to get 3 mu is equal to 3 minus 3 lambda. And now we see that 1 and 2 have the same 3 mu. So if we subtract them, so if this is, let this be 3. So now if we do 1 minus 3, we get that 0 is equal to negative 5 plus 5 lambda minus 3 lambda, which gives us plus 8 lambda. And so we get that 8 lambda is equal to 5, which gives us that lambda is equal to 5 over 8. And so that would be our answer for lambda. But remember, we also need to find the value of mu. So if we substitute that back into our equation 2, we get that mu is equal to 1 minus lambda, which is 5 over 8 as we've solved. And therefore mu is equal to 3 over 8. And that is our final answer for both values. So we've effectively found both the value of both constants. And a quick way to just see if your answer is right is, remember at the beginning I said that lambda and mu must both be less than 1 since they're fractions of a vector. And our answer does confirm that they both are less than 1. And this is a good way to check your answer in a vectors question like this, is by just substituting back in and looking if everything you've solved makes sense. So yes, that is it for this video. I hope this video was helpful. And please do remember that this channel is tailored for individual support and requests. And with the exam season very close now, please use the opportunity and feel free to send any questions you have in particular. And I'll be happy to work through them and solve them like I've done here. But for this video, this is it. Thank you and see you